So if we substitute number of moles is equal to mass over mm, where mm represents molar mass. Put this up here, m equals mass and mm equal molar mass. Okay. So we substitute N for mass over molar mass. So then we get PV equals M over MM, RT. If we multiply both sides by MM, we get rid of the MM over here, and we just get MM located over here. Then we multiply both sides, divide both sides by RT. So we get the RT on this side, and then we divide both sides by V. So then we get mass over volume, which we know is equal to density. Okay. Okay, so let's use this in our next example. How's your week going so far?
I was sick yesterday.
Going well.
We're all sick at home, so
Yeah, me too. I was so sick the whole weekend.
yeah.
And I actually went home sick yesterday. Give me 1 second. I'm in a couple of trouble on my end again. Me and computers lately. Okay, so let me stop sharing. Fix. So what happens when you have 50 things open at once? Okay, there you go. So what is the density of helium at 20? Oh, can you guys don't see, right? Can you guys see it now?
Yeah.
So what is the density of helium at 22 degrees Celsius and 744 torr? So what are we going to do?
Do we convert the temperature to Kelvin?
Okay, we're going to convert the temperature to Kelvin. Okay, so how do I do that? I have 22 degrees Celsius.
To 273.15.
Okay. 273.15. So that's 295 0.15. Okay, what else do I need to do?
Would you need to convert torr to atmospheres?
I need to convert torrs to atmospheres. So I know if I have 744 torrs, how do I convert that to atmospheres?
I think it's oh, right. It's 1 atmosphere is 760 torr.
ATM. $760 torr. And that's going to equal
I got 0.979 sig figs.
okay, 0.979. Okay, torr. I mean atmospheres. Okay, so then what am I going to use? How about,
Do we get the?
what was that?
I was going to say, do we get the molar mass of helium?
Okay, so we need the molar mass of helium. MM of helium equals okay, what is the molar mass of helium? Where would I find that?
The periodic table, so it's 4.0026 grams per mole.
4.
If you wanted to round to 4.
0.00 grams per mole. Okay, so then we know it's going to be the molar mass okay, divided by, or I should say RT. That's right, molar mass. Sorry. Should be RT. Is that correct? Is that the equation that we're going to use? So if the molar mass is 4.0, that's grams per mole. Times the pressure, which is ATMs. So it's 0. 979 ATM. Divided by R, which is 0.0821, and that's ATM liters over Kelvin mole and T, which is 295.15 Kelvin. Okay, so our kelvins are going to cancel out. Our moles are going to cancel out. Our ATMs are going to cancel out. And then we're going to be left with just units of grams per liter. Okay, somebody do the hard math for me.
I got 0.16. 2.
Okay, 0.162.
But we would use 3 sig figs, right?
Yep. So 0.162. Yep.
I have a question about the R.
Okay.
How did you get 0.0821?
It's a constant.
Hmm?
It is a constant.
Oh, so we use that.
Yeah.
Okay.
So long as we're using ATM liters, Kelvin, moles,
Mhm.
that value, that's always going to be the value for it. Now, if we went to torrs, we'd have to convert it to torrs. So then we'd have to do the conversion factor to convert it to torrs.
Mhm.
Okay.
Okay.
So that's why we like to put everything into ATMs so that we can always use that R value. Okay. Clear this. See if I can get my slides to move. Okay, so we also have the term called molecular volume. Molecular volume is just volume divided by moles, kind of like molecular mass was mass divided by moles. So in this case, we can solve for molecular volume by changing around our PV equals nRT so that we'd end up with V over N. And so that's just going to be equal to RT over P. So at STP, the molecular volume is always going to be the same regardless of what it is. Why is that? What is STP?
It's 273 Kelvin, and is it 1 bar or is it 1 atmosphere?
They're about the same, but it's 1 bar to be exact.
Okay, because I was a little bit confused. There's that portion of the book where it was like 22.7 or 22.4 liters.
Yeah.
Depending if you're using atmospheres or
Or
bars.
if you're using a bar. Yeah, because a bar is going to be an ATM. I always forget. So it's 1 bar. And then, so normally it's 1 bar is what we use. But the difference between a bar and an ATM, 1 bar ATM equals 0.01325, I believe, bars. Okay, so that's the distinction between the two. They're pretty much the same, but it's a mild difference. Okay. Okay, so regardless of what it is, if it's at STP, which stands for standard temperature and pressure, then you're always going to be using those same values. So then your volume over moles, or your molar volume, is always going to be that same value. So let's do the calculation. Get my pen up. So we have 0.0821 divided by, that's ATM, liters, moles Kelvin, time temperature, 273, divided by the pressure. So we'll need to convert this to a bar into ATM. So 1 bar is going to be, what is that, 9 point something. Zero 0.987 ATM. $22.7 liters per mole. Okay, so at STP, regardless of what the substance is, it's always going to be the same value, right? Because the only thing that you're going to be dependent on is temperature and pressure. Okay, forward. Okay, so this is just showing you exactly what we just talked about. Okay, so what is the molar volume of air at 11 degrees Celsius and 1.33 ATM? So what am I going to do?
Convert the temperature Celsius to Kelvin.
Okay, so T is going to equal 11 plus 273.14. I mean, sorry, 15. 284.15 Kelvin. Okay.
We already have it in atmosphere, so we will just keep it.
Okay. So then our molar volume is going to equal RT over V. RT over P. Sorry, brain is half working today. So then that's 0.0821 ATM Kelvin, ATM liters over moles Kelvin. Times 284.15 Kelvin divided by 1.33 ATM. So that equals, who's going to do the heavy lifting?
You?
Me.
17.5 liters, liters per mole.
17.5 liters per mole. Okay. Questions? Concerns? Cash? Kool-Aid? Okay.
I guess my question is that, so I don't think I quite understand, like we're able to figure out the molar volume of, what was it, helium?
Mm-hmm.
And then, so regardless of what gas it is at that temperature and pressure, it's going to be 17.5 liters per mole.
That's right. And so that's
Okay.
why we could have a mixture of air. We didn't have to
Right.
specify what it is because it's not dependent on the substance, right?
Right.
It's only dependent on pressure and
Uh-huh.
temperature.
So Charles's law, or is that?
Charles's law? Yeah. Yep.
Okay.
Sort of. Yeah. Okay. So as I mentioned to you guys, we can basically do stoichiometry at STP and at other temperatures as well. If we know, by following this diagram. So, because we can use PV equals nRT to sit there and calculate the number of moles or use the molar volume. And then we can get to the number of moles because there should be a direct relationship, right? Remember Avogadro's law, a direct relationship between volume and number of moles. Okay. So since there's a direct relationship, we can use that mole to mole ratio for a volume to volume ratio to calculate that volume on the other side. Okay. So let me show you what I mean. So what is the volume of hydrogen measured at STP? What volume of hydrogen measured at STP can be released by 42.7 grams of zinc as it reacts with hydrochloric acid? we're going to start with this.
Are given.
Our given, okay? So what is our given?
22.7 grams of zinc.
Okay, so we have 42.7 grams of zinc. Okay. So how can I convert zinc into moles?
Let's see, zinc is 65.38 grams per mole.
So here's a pet crow. That's what it sounds like.
There might be a bird out my window.
Okay.
Did it sound like a crow?
It sounds like a crow or a blackbird.
Okay.
I recognize their tone anywhere. When I was a kid, there were these group of blackbirds that used to chase me to school. I don't know if you guys have ever seen Damien. It's an old horror movie. It always reminds me of that movie.
Was that produced by Stephen King?
I don't think so. I could be wrong though. Okay, so this would give me the moles of zinc, right?
And then you would use the mole to mole ratio of zinc to hydrogen.
Okay, so then I can use the mole to mole ratio of zinc to hydrogen. Okay, so we know that
0.65.
0.65.
We use it in the same.
3. What was that?
We use it in the same equation, like the mole to mole ratio.
Yep, we could use it in the same equation if we wanted to. We could have kept on. But I wanted to show you this first, right? So the mole to mole ratio of zinc to hydrogen gas is a 1-to-1 ratio. Is that correct? So we know that the molar volume is what for at STP?
Oh, 22.7.
So we know that the molar volume equals 22.7 at standard
liters.
temperature and pressure. Yep, liters per mole, right? So then I can use the molar volume just by multiplying by the number of moles, right? So I'd have to use that mole to mole ratio, which I know is a 1-to-1 mole to mole ratio. So I'll go 653 moles of zinc. We know that's a 1-to-1 mole ratio. 1-to-1 moles of zinc to moles of hydrogen gas. And then I can use this value over here to convert to liters. So 2.7 liters moles. Okay,
14.8 liters.
okay. Piece of cake. Okay. Let me clear. Then we can move forward. So that's one way that we could use. So the other way that we could have done is actually just calculated the number of moles and then plug that into PV equals nRT, right? So that would be the other way. So how many moles, or say how many liters of carbon dioxide measured at 744 torrs and 131 degrees Celsius will be produced by the complete burning of 16.2 grams of gaseous butane? The equation is 2 butanes plus 13 oxygens yields 8 carbon dioxides and 10 waters. Okay, so what are we going to do?
Name your pressure and your temperature.
What was that? Okay, I want to change my pressure and my temperature. Okay. So let's do temperature up here. So we know it's 131 plus 273. It's 304.15. I forgot my 1.5 Kelvin.
I got 404.
Oh, yes, it is right. 404. I was just testing you out. I'd have been 100 degrees off or 100 Kelvin off. Okay. And then P, do that here.
Should you do 744 divided by 760?
Yep. ATM. That equals what?
0.979 ATM.
Okay. Okay, so we've done that. That gives me my pressure. That gives me my temperature. It says how many moles of carbon dioxide measured at 744 torrs and 131 degrees Celsius will be produced by the complete burning of 16.2 grams of gaseous butane.
So you need to find The molar mass of butane,
I need to find the molar mass of butane. Okay.
which would be carbon's 12.011 grams per mole and hydrogen's 1.008 grams per mole.
Okay. So I have 4 times 12 for my carbon, since I have 4 carbons. And you told me I have 10 hydrogens. 1 times 10.
58.
58 grams per mole, roughly. Okay. Then what am I going to do?
The molar
So
ratio?
Mole ratio. That is correct. So we have for every 2 moles of C4H10, we have 8 moles of CO2. Okay. It's going to do the heavy lifting for me. Repeat that, please.
1.12.
1.12 moles
Of CO2.
of CO2. Okay, we want the volume. Can we calculate that?
Oh, 22.7. Or no, sorry, that's SDP. This is
So
molar
you're telling me I
volume.
need to calculate the molar volume at this temperature, which is going to be
Right.
equal to,
So 0.0821 times
okay,
404.15 Kelvin over not 0.979 atmospheres.
okay. So what do we got?
I got 33.89. Liters per mole.
Okay. Okay, so then we could just multiply our number of moles by that volume. So 1.12 moles of CO2 times our volume. I mean that molar volume, sorry, 33.89 for 1 mole. And then that equals I know my handwriting is horrible. That's a 2, not a 7.
Is that a V or an L?
That's a, oh, sorry, that's an L. It should be an L. Good eye. I was thinking volume. Instead of putting liters, I put volume. $33.80. Sorry. 30. I cannot even. 38.80. Right. 38.0. I can't even talk. 38.0 liters. What did you guys get?
38.0 liters.
Okay. Okay, questions? Robin, you had to look at the question.
What was so when we're calculating the molar volume,
Uh-huh.
what would be our sig figs? It would be 3, right?
That should be 3. So that should be 33.9. Yes.
Okay.
Yeah.
And then for grams of butane to moles of CO2,
Uh-huh.
I got 1.11.
1.11, not 1.12.
Yeah, but I
What was it? What was the number following the 1?
1.11.
I know, but what was the number following the 1 after you got it? Was it a 5 or greater? Or did you just get exactly 1.11 exactly?
16.2 divided by 5.
I got 1.117.
So then you'd round it up, right?
16.2.
Correct. So you get 1.12.
4 times 8 divided by 2. No, sorry, I don't follow.
You don't follow? So the number that you get here is 1.117.
1.
Right?
Oh,
So since that's a 7, then that's going to be a 2.
okay.
So it's
Oh,
1.12.
okay. I think I'm okay.
But if it's a 5, you can leave it at neutral as 1.11, right?
If it's exactly 5 with nothing following it, then
I
yeah,
have it.
you leave it as 1.11. But if there's a number here, even if it's 0.2, then you're going to round it up.
I have different sig
Okay,
figs
thank
for the butane because I'm using it all the way like the 3 decimal places. So I think that's where I went That's where my computation, I was just wondering if I did something drastically wrong, but it looks like no.
No. Did you end up with 38?
Basically, yeah.
Yeah. Okay. Okay. Let's move forward. Okay. Okay, so we've gone through it, and then, as I said, we can also use the ideal gas method. It's essentially the same thing. So rather than multiplying by the molar volume, we just plug it into the ideal gas law for it. Right? So I'm not going to go over it. You guys can look over it yourselves. It's just another way of doing the same problem. Okay. Okay, so we've already talked about volume being proportional and to the number of moles. So we can kind of take advantage of that for the chemical equation, right? So it says here, it was found that 1.75 liters of oxygen measured at 24 degrees Celsius and 755 torr is used in burning sulfur. At one point in the exhaust hood, the sulfur dioxide produced is at 165 degrees Celsius and 785 torr. Find the volume of sulfur dioxide at these conditions. Okay. So what do you think we're going to do?
Convert the temperature.
Okay, so convert our temperature. (24 Celsius plus 273.15 equals 297.15 165 degrees C plus 273.15
438.1.
38.15.
Dr.
Yep.
The 297.15, that would be T1, right?
Yep. You're starting.
And T2 would be the 165 plus 270.
Good job. Yep. Okay. So, excuse me. What else do we have?
Your P1 would be 755 torr divided by 160.
Okay. 755 torr
So are we going to use the combined gas law to,
Sorta, yes. But we also have to take one other thing in consideration. Although it
Okay.
works out perfectly in this circumstances, but not always. For 1 ATM. And that equals
0.993 ATM.
and then P2. Guess we didn't need to change these, but okay.
1.03. ATM.
Okay. So if we use the combined law PV, P1, B1 over T1 equals P2, V2 over T2. The other thing that we have to take in consideration is that here we're talking about oxygen, right? And so we would need that conversion, the mole to mole ratio of oxygen to sulfur dioxide. So just so happens that this would give us the number of moles of oxygen. And then it would be, I'm going to put NO2 at the bottom over N, so right, NO2 over N SO2. Okay, so you would need that ratio. Just so happen it's 1-to-1 in this case, right? So then we just solve for V2. So we'll get P1, T1, P1, T1, P1, and that would be N. Oh, that switched. Sorry, I have that. N. Sorry. NSO2. NO2. And this is P2 over T2, or T2 over V2. And that's going to equal our B, B2. Sorry, that should be P2 down here, since we're looking for volume. Sorry, hands half working today. So we plug in those values.
That wouldn't be switched though? Wouldn't it be P2 on the top and T2 on the bottom?
No, because we have V1 over here, right? V1, P1, V1 over T2, P1, V1 over, I'm sorry, P1, V1 over T1, P1, V1 over T1. And then when we bring this over to the other side, that's going to bring the T up top, T2 over top. Does that make sense?
Because you're doing the mole-to-mole ratio.
Well, it's not only because we're doing the mole-to-mole ratio. We have the mole-to-mole ratio incorporated here, right? Just really, let me take one step back. Let me erase. So, actually, I'm going to rewrite something out. So we have R is going to equal N T over PV. Right, actually, that's wrong. Backwards today. PV over NT. There you go. Okay. So, because we know that PV equals nRT, right? So R is a constant. So if we set these guys equal to each other, this here represents the number of moles that we're starting out with, right? Or our N1, which just happens to be oxygen, compared to the number of moles that we end with, which is the sulfur dioxide, right? Which is going to be our N2. So if we set these equal to each other, okay, and then we're solving for V2, right? So that means that we're bringing all this stuff over to the other side. We basically end up with this, our P1, V1, N SO4, which is our N2, right? Times our T2, divided by our T1, P2, and our NO2. Does that make sense? Or do you want me to, let me work it out on the side so you'll see it. So we solve for, these are all ones. Excuse me. Okay, so what I'm going to do is I'm going to bring over all of these guys. So I'm going to multiply both sides by the inverse of this. So then that's going to be P2 at the bottom, N2 at the top, T2.
And you wouldn't transfer the V because we're trying to find the volume.
That's right. And then we're just going to end up with just the V over here, right? Because all of this stuff is going to cancel out on this side. And so our N1 is just going to equal the number of moles of oxygen, O2. Our N2 is going to equal the number of moles
Sulfur dioxide.
of sulfur, right? Okay, so we need that mole-to-mole ratio. In this case, it's a 1-to-1 mole-to-mole ratio, right? So then we just get, that's the case, these guys are going to cancel out, and we're going to get V2 is just going to equal
P1,
P1, V1,
T2.
T2 divided by oops, T1,
P2.
P2. That's right. Okay, so if we go ahead and plug that in, P2 is going to equal
So we need to find V1.
no, it's given to us right there.
Oh, okay. So missed that.
Times 1.75. Can I erase this right here?
Mhm.
This hot mess. Times T2, which was 438.15 divided by T1, which was 297.15. Oops. Times our P2, which is 1.03. Okay. Okay, what did you guys get?
2.49 liters of sulfur dioxide.
2.5.
Okay. How many sig figs should we have?
3.
Okay. Okay. I love the speech to text at the bottom. It says, how many sigs should I have? Instead of sig figs. Okay. Question marks?
Professor,
Yes,
if it did have like a different molar ratio, say like 3 to 2, you would have to write that into the equation.
that is correct. You see where we have our ends here? We put those in there.
So would you write like the 3 mole SO2, for example? Would you
Yeah, so
write it down like that?
let's just say that this was really sulfur 8, right? Here. So then that means that this was S8, right? So then we would have to balance the chemical equation. So let's do that real quick. Let's balance this chemical equation. So that means that we would have 8 of these and then 16 of these, right? Okay. So then our O, it's horrible. Sorry. Let me fix this so it doesn't look so bad. 1, 6. Okay. So, and this is 8 here. Okay. So then our ratio
Wouldn't the coefficient be 8 in front of the oxygen?
oh yeah, you're right. I'm sorry, my bad. Thank you. So I guess it works out same either way. Yes, that would be a balanced chemical equation. Yes, today is not my day. So that would be 8 16, 16. Okay, so then that would be a 1-to-1 ratio as well too. Damn it. I need another way. But let's assume that it wasn't 8. Let's say this was put a 3 here. Is that better? So we'll make it
Would that be
ozone.
ozone? Yeah.
Yes. Make it ozone. Okay, so then the ratio would be different, right? And so it would be the ratio of that difference. That's what we put in for these ends. Does that make sense?
Yeah.
Okay. So that's the reason why I wanted to show you that, because, you know, it's perfect when it's, you know, a 1-to-1 ratio. But when it's not a 1-to-1 ratio, you have to take in consideration the difference in that ratio. Okay.
You would just balance it.
That's right. Yeah, and then for your ends, you're going to plug in those values, right? Because then all you're doing is converting, you're changing those ends over to what they should be. So, okay, so chapter 15, gases, liquids, and solids. Okay, so we're going to fill in some gaps that we have a little bit. So one of the things that we will talk about, or going to talk about, are partial pressures. Partial pressures are just partial. Let's say if we have a mixture of gases, gas like air, right? So partial pressures is just the pressure of each of the gases individually, and that's going to sum up to a total pressure, which we call just P. So P is going to equal P1, P2, P3, P4, P5, P6, as many different gases that we have in there that aren't reacting with each other. Okay, so can you guys see the screen? Yeah, I don't want to get halfway through it and then realize that we're done. Okay, a scientist sets up an artificial atmosphere with 4 gases. Their partial pressures are 0.78 bar nitrogen, 0.21 bar oxygen, 0.009 bars argon, and 0.025 bars water. What is the total pressure? So P total. Okay, so we know P total is going to equal P1 plus P2 plus P3 plus P4.
When you're
Oh, go
putting
ahead.
the pressures, do we need to name them, like 0.78 nitrogen?
You won't have to name them. I mean, because that P1 represents the nitrogen, 1 represents nitrogen, 2 represents, because these gases aren't interacting with each other, they're not, in theory, if under ideal circumstances, they're just bouncing off of each other. They're just both all being stuffed into one bottle. Does that make sense? So for instance, if I put helium in a balloon, and then I put oxygen in that same balloon, and then I put nitrogen in that same balloon, well, those guys aren't going to react with each other. They're just all going into a balloon together, but that pressure is going to increase because I keep adding that to the balloon. Okay.
Would it be 1.02 bars?
That is correct. After we add them all together, yes. And you can leave them in bars. You don't have to change it to ATM in this case, because they're all in bars, right? Those are good questions. And what did you get again, Robin?
I got 1.02, when you're adding, you just line everything up to the decimal point, and then you go to the shortest number, right?
That's right.
Okay.
Well, let's see. 1, 2, 3. Actually, it should be 1.03, shouldn't it?
1 point.
I got 1.02.
So if we added it all together, right? So let's go.
I got
7.
0.024.
Yeah, that's what
2,
I
4?
got. And then because you're adding, I took off the 4, but I wasn't quite sure if I was doing that right.
Oh, sorry. Yeah, I see. I've added one too many zeros here.
Oh.
Yeah. So, 2. Yep, 1.02. Okay. Questions? Concerns? Okay, good. So this is just showing us an example. So if we just looked at the partial pressure of nitrogen, and then this is the partial pressure of oxygen, and if we mix those two gases together, then this would be the partial pressure of both of them added together, which would just be the sum, right? Questions? Okay.
Is 1 millimeter of mercury the same as 1 torr?
Yes.
Or, okay.
Yep. Okay, so this is a quick way of setting up those experiments. You guys did gas experiments. They were sort of done this way. Remember where they were bubbling into our test tube or into our beaker, and things did not work out the way they were supposed to, right? So this is just showing you how to set up that apparatus. You guys were ahead of the game. Okay, so the next thing that we're going to talk about is it's also called vapor pressure. So that partial pressure is also considered to be the vapor pressure. Okay, so in this case, we have the total pressure is going to equal the pressure of the gas plus the partial pressure of water. Okay, or the vapor pressure of water. Okay, so in this case, the water level inside and outside of the test tubes are going to be the same to equalize that pressure. And then, and that's because the water level in the tube and the pan are going to be equal to each other. Sort of like what we did, only thing we kind of set it up a little bit differently because we put in more water up in our tubes. You guys remember that? And then we pushed out that. So in that case, that wouldn't be the vapor pressure. We would just have the pressure of the gas and using that as our volume. Does that make sense? Okay, calculate the partial pressure of oxygen in ATM in a sample that's collected over water. Given that the partial pressure, given that the total pressure of the mixture is 0.98 ATMs, and the partial pressure of water vapor is 16.5 millimeters of mercury. What is the first thing I need to do?
Convert your millimeters into
Okay,
Get one to the other, I suppose.
yeah, but they
Or-
wanted it in ATMs, so we should probably convert everything to ATMs, right?
Oh, okay. Yeah.
So you just told me that a torr and millimeters of mercury are the same, so 760 millimeters of mercury is going to equal 1 ATM. So how many sig figs?
3.
2.
3.
Oh, is that?
This
Oh,
is a
okay.
big-
It's a perfect number, right?
Yep.
Okay.
Okay. So then we know that PO is going to equal, sorry, PO2. It's going to equal total pressure minus pH2O. Okay, so that's going to equal 0.98 minus 0.021. 7. Okay, so that's hold on 1 second. Do you want me to come see you afterwards? Okay, so that's 3, 8, 5. Okay, so how many sig figs should I have?
3.
So should it be 2? It'd be 0.96 because this only went out to right here. And so if we were lining up, we'd use that 8 to round up. Make sense? Okay. Okay, so we compare liquids to gases. We know that gases are able to compress where liquids can't. Gases are able to expand to fill that container where liquids don't. We know that gases are low density. Liquids are relatively high density. Gases, they can be mixed to a fixed volume. Liquids can't. And gases are going to exert constant pressure on the walls of the container uniformly, where pressure in the liquid container increases as the depth increases.
Is that why the lower you get, the more pressure there is?
Yes. Yeah. Okay, so vapor pressure, we know that vapor pressure is just going to be that partial pressure, or the pressure that's going to be exerted by the vapor that is in contact with that liquid phase. So it's just that pressure that's at that surface of the liquid phase. Okay, so like when we put that tube on the water, that the bubbler, right? So then the phase where you have that intersection is where you're going to have your vapor pressure mostly being, and that's going to be able to capture all of the vapor pressure that's inside that tube. Okay, so if the gas space above the liquid is closed, then the vapor pressure is going to increase to a definite value, which is called the equilibrium vapor pressure. So if we sit there and we seal it so that it's not able to get out anywhere else, that vapor pressure is going to reach a point of equilibrium, essentially. And so that basically means that the rate of the molecules of water that are going up are going to equal to the rate of the molecules that are going down, meaning the stuff that's going up into the vapor is going to be equal to the ones that are going back down into solution. So that change is going to be equal to each other. Okay, do you guys understand that? So let me give you a drawing here. Hold on. Wonder if I have it. Nope. Okay, so here's our tube, right? Here's the water. Okay, now molecules are going to be going up and going into the gas phase, right? And then we're going to have molecules that are going to be going down back into the liquid phase. Now, the rate of the molecules going up when it reaches equilibrium is going to be equal to the rate of molecules going down. So those rates are going to be equal to each other. Okay, so when things are in equilibrium. Okay. So that means that you're going to have a consistent vapor pressure that's associated with it. That consistent vapor pressure, that's going to be called your equilibrium vapor pressure. Okay. So depending on how the day is and everything like that, right above the a lake. So if the temperature is at 70 degrees, the rate of stuff that's going up is going to be consistent to the rate that's going back into solution above that lake. Okay. Now, the stronger the intermolecular forces, the attractive forces, the fewer number of liquid particles are able to escape into the gaseous phase. So if you have a lot of intermolecular forces, things are going to stay in that liquid phase stronger, better than it will be if they have weak interacting forces, right? So what do I mean by weak interacting forces? So let's say in the case of water, we know that oxygen is more electronegative than hydrogen. So because oxygen is more electronegative than hydrogen, oxygen is going to get a partial negative charge associated with it. And hydrogen is going to have a partial positive charge associated with it. Okay, so if this guy is partial positive and this guy is partial negative, they're going to form what we call a hydrogen bond. That's an interaction. So a hydrogen bond is like a fist-to-fist interaction. You know, we can put it fist to fist, it can be pretty strong, right? But it's not connected. It's not like a covalent interaction. It's a strong interaction, but it's not the strongest interaction. Okay. So they form what we call a hydrogen bond. So this represents that hydrogen bond. Okay. So this here is called intermolecular forces. So these guys are interacting with each other, and they're interacting based upon those partial charges. Even though they're not complete charges, they're strong enough to get an interaction. They're able to make that connection. Okay. Now, the stronger these are, the more of these that you have in a molecule or something like that, the harder it is for it to go into the gaseous state, meaning that it takes more energy for it to go into the gaseous state. Okay, so let me give you an example of that. So this is just basically showing you. So the process of water going into the gas phase is called evaporation, right? It evaporates. Okay. So this here shows us that water coming back into the liquid phase. This is going into the gas phase. Okay. So these, if you take a look at these guys are all going into the gas phase. These guys are coming back. Okay. Liquid phase, gas phase. Okay. So because of this interaction, the hydrogen bonding between these guys interacting with each other, it makes it harder for these guys to escape into this phase, right? If there weren't interactions, strong interactions, they would be easily able to escape, okay? So the heat of vaporization, so do you guys remember the heat of a reaction? Delta H, we talked about it at the end of chapter 10. So this is delta H vape. Okay, so the heat of vaporization is defined as the quantity of energy required to change 1 mole of liquid to its vapor while at a constant temperature and pressure. Okay, the stronger the intermolecular forces, the higher the heat of vaporization. So in other words, if you have really strong forces, let's say you have a positive and negative charges that are keeping things together, it's going to be really, really hard to vaporize it. It's going to be hard to make that into a gas. Okay, but the weaker it is, it's going to be real easy to make it into a gas. Okay, so that's part of the reason why, like, methane is a gas, where let's say we have pentane. Pentane is a liquid. Pentane is 5 carbons. Pentane. Methane is 1 carbon. Methane, pentane. Okay, 5 carbon. So 5 carbon chains, because of those 5 carbons, they're interacting with each other, and they're using what we call van der Waals forces. Those are really weak interactions, but there's so many of them that kind of keep them together. So it takes a little more energy, or actually it takes quite a bit more energy to sit there and make this into a gas. Well, we know that methane is a gas at room temperature because there's so little interaction between each of the methane molecules. You have that? Yeah, right.
So what's going to make it harder for it to evaporate is the change of the temperature. It's harder for them to reach that temperature state where it evaporates.
No, so what makes it harder for it to evaporate is if there are a lot of forces, a lot of intermolecular forces between the two molecules. So for instance, this here is CH4. This here is C5H. What's that? So that's 12. Okay, so it's C5H12. This guy is really, really long, and so it interacts with each other. Each of the molecules are really good at interacting with each other, right? Where this guy doesn't have too much to interact with. It only has that carbon and those hydrogens to interact with. this has 5 carbons altogether. So it'll be 1, 2, 3, 4, 5 carbon chain, right? So this 5 carbon chain is interacting with this 5 carbon chain, which is interacting with this 5 carbon chain. So there's a lot more points for this guy to interact, where you just have, in this case, it's just methane. It's just that carbon by itself, right?
So that one carbon is just.
Yeah, it's not enough to hold it together, so it's already in a gaseous form, right? Where this guy is enough for these guys to interact with each other to hold each other together. Okay, and the stronger forces that you have, like hydrogen bonds or ionic bonds, the stronger those are, they put things together harder. So it makes it harder to sit there and separate. Like for instance, if I put salt in water, well, the heat of vaporization is going to be a lot harder when I put salt in water than when I just have water by itself, because it has those plus and minus charges that helps hold that water in place. Okay. So the boiling point is the temperature which the vapor pressure becomes equal to the, it's going to be equal to the pressure above the liquid. Okay. So it's the temperature which the vapor pressure becomes equal to the pressure above the liquid. Okay. So that partial pressure that's directly above the liquid, when that vapor pressure becomes equal to that, that's going to be the temperature. That's where you're going to get boiling. So at higher elevation, you have more pressure or less pressure?
Less pressure.
Okay, we have less pressure at higher elevation. All right, I have to think about that. I'm gonna have to look that one up. So if I have a higher pressure, right, then it's gonna take more to get it to boil, right, than in the case where I have a lower pressure. Does that make sense? So let me. Okay. So let me give you an example. Okay, here's a mountain, right? This is me. That's me at the bottom of the mountain. This is where I want to be by the next day. Now, I'm going to have breakfast, and I always have to have my coffee. So if I have my coffee here, is it going to be harder to boil here, or is it going to be harder to boil here at the top of the mountain? This is lower altitude, so this is going to have higher pressure. This is going to have higher altitude. This is going to have lower pressure. So which one is going to boil faster if I'm using the same temperature?
Low pressure.
Low pressure. That is correct. Okay. Does that make sense?
Yeah.
Okay. Now, the reason that's going to be the case, which is going to take less temperature to boil, it's going to be because, well, one thing is PV equals nRT. These guys are going to have to be directly proportional to each other. So if this guy, if I increase in pressure, that means I have to increase in temperature. Right? You see how this always comes back? All right. So if I have lower pressure, then that's going to be lower temperature. Okay. Okay, so take-home message: the stronger the intermolecular forces, the higher temperature you're going to need to separate the particles in that liquid. How you guys doing? Good so far? Okay, good. Okay, now if I can get my slides here.
Is much easier.
You said today is much easier?
No, the day class during the day lecture is much easier than night.
Oh, okay. Sorry. Okay, so this is just showing you what we talked about. So the heat of vaporization, that delta H of vaporization, that one is going to be the same as the heat of condensation. Only thing, they're going in different directions. One is going to be endothermic, one is going to be exothermic. Okay. Make sense? Okay, so properties of liquids. So viscosity. Viscosity is just defined as the resistance of a liquid to flow. So the higher the viscosity, the harder it is to flow. Okay, so which one is going to have a higher viscosity? Syrup or water?
Syrup.
That is correct. Which is going to have a higher viscosity? Water or oil?
I think water. Well, I don't know, because you use oil to lubricate things too. So
Think about pouring a thing of oil out, a quart of oil into your car.
Okay, so then yeah, the oil would be more viscous.
Yeah. Okay, so what's dictating this is also going to be those intermolecular forces. So those forces that are interacting between two molecules. Okay. So the more interacting you have, the greater the forces. So if I have, oops. So we have water. We have let's see, it's triglycerin. Okay, which one of these are going to be more viscous? This here is a long carbon chains with OHs on the end of them. And these are all connected, just branches.
Is that pentothal?
No, it actually would be something more. So that's 1, 2, 3, 4, 5, 6, 7, 8.
Oh,
9,
the whole.
10, 11.
Okay.
Yeah. Okay. And then you'd have off your branching, you also have another branch that also has another output. So, but if you look at the structure, these here are going to be able to form hydrogen bonds, right? Similar to what you form with water, but they're also going to form what we call van der Waals forces, where basically things that are non-polar interacting with each other. Because you have a lot of these guys, long chains, hydrocarbon chains, they're going to interact with each other. So it's going to make it harder for them to be separated because of those interactions.
So like the pentane because there's just more of these or
Carbon?
intermolecular forces.
That's right.
This is going to be more viscous, or
Yeah.
and then greater surface tension.
That's right. So exactly. So it's going to have greater surface tension, and it's also going to be more viscous, okay, because you have interaction, okay? So surface tension is the tendency of a liquid surface to minimize, to have a minimal surface area. So in other words, like that bubbling, okay? So it's basically molecules interacting with themselves rather than that are the same, rather than interacting with things that are different, right? So that's going to form what we call a surface tension on the top, okay? So the stronger the intermolecular attractive forces, the stronger that each particle is attracted in all directions by the particles around it. Okay, so this is example of the surface tension. Okay, so we're basically looking at the molecules interacting at the surface of the molecule, interacting with all those things that are around it. Okay, so here are some substances. We have mercury, we have water, we have benzene, we have ether, and we have ethane. These are the vapor pressures that are associated with each of them, right, at 20 degrees Celsius. So mercury has very little vapor pressure. So what would that mean about mercury if it has very little vapor pressure?
It has low temperature.
Let's assume that this is all done at the same temperature, at 20 degrees. What would that mean about the forces that are acting on it if it has low vapor pressure?
It's basically why mercury is weird. It has the stronger intermolecular forces.
That's right.
And that odd sheen to it, or I'm thinking of the surface tension. Like it looks.
Yes. Have you ever played with? Well, you guys probably have not. So back in the old days, they used to have mercury thermometers when I was a kid, and we used to break the mercury thermometer to play with the mercury. And that's probably explains why I'm a little weird, because as a kid I played with mercury, and so you'd play with it, and as you pushed it apart, it would try to find a way to coming back together because of that surface tension, right? They're attracted to each other, they're so interactive with each other. Okay, because of that, it's also pretty viscous. It also has strong intermolecular forces, where ethane, which is just two carbons that are connected, those are going to have weak molecular forces. These guys are going to be weaker in molecular forces. They're also going to have higher vapor pressure, right? Because they're going to be easily ripped apart compared to the mercury, which is going to have those interactions. Okay. The heat of vaporization, so the energy that it takes to vaporize it, right? So this one, it takes a lot more energy to vaporize it. It's 59 kilojoules per mole. This one is water. That's 41 kilojoules per mole, where it takes 15, it takes less energy to make it a vapor. Its boiling point. Well, ethane is a gas, right? So at room temperature, it's already a gas. So for it to boil, it has to be negative 89 degrees Celsius. Ether, 35 degrees Celsius. Benzene, 80 degrees Celsius. Water, 100 degrees Celsius. And then mercury, 357 degrees Celsius. And that's all because of those forces. So these are three things that are going to be affected by those intermolecular forces. So let's talk about those intermolecular forces. So the two major forces that we're going to be, well, actually there's a couple. One is called the dipole force, right? And so that's a positive pole. So you have something that's a polar molecule that has a positive and a negative pole, right? So for instance, if we have chlorine and hydrogen, okay, so this guy is going to be partially negative, and this guy is going to be partially positive, because we know that the electronegativity is going to pull the electrons towards the chlorine, and then that means the hydrogen is going to get that electron less than that chlorine, that uneven sharing, right? Induced dipole. So induced dipole is basically saying that if I have a negative charge here, let's say I have calcium, a calcium ion, and I put that next to this chlorine hydrogen molecule, it's going to pull the electrons in this direction because this guy's going to want to interact with this guy. Okay, so it's induced. Okay, it's causing it to interact. Or if I put a negative charge next to this, a fluorine ion, right? It's going to, if I put it next to it because electrons are here, it's going to push those electrons over to the hydrogen. Okay, so that would be an induced dipole. Okay, and then I showed you what hydrogen bonding was earlier. Okay, now this here is the strongest force, right? These guys, they're pretty good, but this one is just kind of induced. It's a temporary, right? These guys are more stable than this guy is. Okay, so here's an example of our dipole force. So as I said, this guy, in this case, we have bromine chloride. Well, chloride is more electronegative than bromine. So then the electron is going to be spending more time with the chlorine than the bromine, right? And these guys are going to interact with each other because of that. This guy is going to be partially positive. This guy's going to be partially negative. This guy's partially negative, partially positive. Now that partial positive is going to interact with, that partial negative is going to interact with that partial positive, and vice versa down here too. Okay. So here's some examples. If we have nitrogen gas, that's nonpolar. We know its molar mass is 28. Its boiling point is negative 196. If we have carbon dioxide, which is polar, carbon monoxide, which is polar, it has the exact same molar mass, but its boiling point is 192. So its actually boiling point is higher than the boiling point of the nitrogen gas. Here we have silicon tetrahydride. This guy is nonpolar. Its molar mass is 32. Its boiling point is negative 112. And then we have phosphorus trihydride. That guy is polar. Its molar mass is 34, and its boiling point is negative 88. And so if we take a look at, we have iodine chloride, which is polar. It's going to be 162, and its boiling point is going to be 97 degrees Celsius, where the bromide is going to be nonpolar. Its molar mass is 160, and then it's going to be 59. Now, we sit there and we think about it, those things that are more polar, right, are stronger, right, because they have those stronger interactions compared to what we have with those nonpolar ones. Okay, so two nonpolar molecules, right? This is basically where their starting point. So what happens if they're both nonpolar, and then one gets slightly induced, so then that's going to slightly induce this other guy, and then you're going to get interactions this. But this is such a quick moment. So this is the example of the induced dipole. We've induced this guy to interact by this guy being negative, and then that's going to cause positives to come over here and that negative to go the other way. So the electrons are going to go the other way, this guy's going to become positive. So this is going to induce this other guy to happen. But again, this is only a temporary thing. Okay, now recognizing hydrogen bonds, these guys are always going to form strong hydrogen bonds. So if you have hydrogen next to a nitrogen, hydrogen next to an oxygen, hydrogen next to a fluorine. Okay, so these guys are always going to form strong hydrogen bonds. Everything else is considered dipole. Okay, now here's water, here's ammonia, and here's methane. So water's boiling temperature is 100 degrees. Ammonia's boiling temperature is about negative 15. And then we know that methane is like negative 100 and I don't know, 40, something like that. Okay, so there's clearly a distinction between it. Now, if we take a look and we substitute, instead of putting oxygen here, we put sulfur. That drops the boiling point greatly, right? And that's because we know that sulfur has a weak electronegativity compared to that of oxygen, right? The electronegativity of sulfur and hydrogen are almost the same. So that means that they're sharing more evenly than the case of the oxygen and the hydrogen. Okay. And then it gets better as we go down because other factors start to come into play. And so you get more interactions that are happening. Okay, questions? Okay, good. So this here represents the kinetic energy curve for a liquid. So this represents the kinetic energy. This is the percentage of molecules with that given kinetic energy. Okay. And this is at a given temperature. Okay, so let's assume that this was at 25 degrees. So what this basically means is that most of the molecules are going to be here, but they're going to be distributed along this energy curve, right? So most of the molecules are going to be at this kinetic energy, but there's going to be a distribution of them along this energy curve, okay? So the goal is for evaporation to occur, you have to be over what we call, it's kind of like a threshold energy, right? And this E represents that threshold energy. If you're not above that threshold energy, then you won't have evaporation occurring, okay?
So if I'm boiling water for my pasta,
Yes.
so like there's only so much amount of water that's going to be vapor, and then the majority of it is just still has energy, but it's still in liquid form. Is that
Okay,
right?
so let me kind of put it more. So we're boiling water for our pasta, but we put it at 25 degrees Celsius. Now water boils at what temperature?
100.
Okay, so we have our water boiling at, we'll say 30 degrees Celsius, right? So that's never going to get hot enough to boil our pasta, right? But there's going to be so many of them that are going to have enough kinetic energy, right?
Oh, anyway.
That's right.
Okay.
So we're going to have so many of them that are going to be in that vapor part, but not that many, right? And then, but as we increase that temperature, what we've done, we're increasing that kinetic energy. So then we're shifting the number of molecules to be over that threshold.
I see.
Okay.
So
we're doing this. So as temperature increases, we're doing this.
Right. I just find it odd that like even at like 25 degrees, there are molecules that have enough energy to be in the vapor state. But I guess that's nature.
That's that partial pressure. That's that equilibrium. Yeah.
Okay.
You know, you have that one molecule that's just all hyped up, you know. like that one kid in the class that is always bouncing off the wall. Okay, so we have what we call the liquid vapor equilibrium. So again, that basically means that you're going in both directions. We've already talked about this, going in both directions, right? So, and this just is basically showing you that, right? So this is before equilibrium is reached. This is as we're getting closer to reaching equilibrium. As we're getting closer to reaching equilibrium, this is the point where equilibrium is essentially reached, right? And so you kind of see right here, that's where the two of them come together. So that rate of evaporation and condensation is going to be exactly the same. Okay. And you guys can see that. So here, condensation is increasing, and then our evaporation. Okay. And so at equilibrium, that's when both of them, the rate of condensation and the rate of evaporation are going to be the same. So that's considered equilibrium. Okay. Okay, so here we have, okay, so here's water. Here is ethanol. Here is diethyl ether. Diethyl ether here, it's a bigger molecule, right? But the thing is, there's not a lot of hydrogen bond that goes on here. You only have this oxygen that's attached to both carbon and carbon. So these guys are not interacting very well with each other. These are just carbons. Carbons are going to have a very weak interaction, but they're not going to be as strong as a hydrogen bond. Water has a lot of hydrogen bonding. Ethanol has a little bit of hydrogen bonding. So its normal boiling point is 78.3, where water is 100. Diethyl ether, its normal boiling point is 4.6. Okay, so this is what we were talking about in terms of that higher temperature. So T is higher than T1 is lower than T2. So then at the higher temperature, you're shifting your equilibrium because you're increasing that kinetic energy, right? So you're going to get a shift in that curve. Okay, so we already know what boiling is. So basically where the process which a liquid undergoes a constant temperature transition to a gas because of the transfer of energy. So in other words, put in energy to sit there and change that phase. Okay, so the normal boiling point is the temperature at which a substance boils in an open vessel that is 1 atmosphere pressure. So we know that if the vessel is open to the air, for it to boil, it has to be at 1 atmosphere. Or I should say, it should be the temperature where we're getting it at 1 atmosphere. And this is just basically showing that. So the unusual properties of water, it has a high boiling point. Among molecules comparable in size, water has a high surface tension. It has a higher heat of vaporization. It has a low vapor pressure, a higher viscosity. It dissolves many substances. The liquid state at room temperature and pressure, and it forms a solid that floats on the liquid. Okay, so here's a water molecule. We know that the angle is 104.5. We kind of talked about that a little bit. It's different than what we would normally expect because we would expect it to be like 109.5, but it's in a little bit tighter because of those interactions. And then those lone pairs that are kicking up here, right? So we have those two lone pairs on top of those oxygens. And that's going to shift our angle. So a crystalline solid. So a crystalline solid basically is a solid that is organized. It has a very defined geometric pattern, where an amorphous solid is one that is unorganized. It's kind of randomly ordered. Okay, here's examples of crystalline solids. Okay, this guy's considered to be amorphous. It's not really organized, it's just kind of randomly linked. Okay, so here's an example of a crystalline solid that's basically being chipped. You know, so you're getting these nice little beautiful chips of that crystalline solid. This here is the breaking of glass, of a mirror. And then in this case, this kind of gives us an example of an amorphous solid. When you break it, you don't know what's going to happen, right? We're here, we chipped it, we got these nice chips that are forming. So you get these nice little chip flakes coming off of it. We could have ionic crystals, we could have molecular crystals, we could have covalently networked solids, we could have metallic crystals. This here is an example of an ionic crystal. So this basically is a rock. You know, most rocks are made up of ionic compounds. Here, this is sulfur. So this is sulfur all by itself. It's a nice powdery form. And then here, we've heated up sulfur, and it actually forms this amorphous network, randomly organized. So these are all quartz crystals. So in other words, these are, I want to say aluminum, not aluminum oxide. Actually, yes, I think quartz is aluminum oxide. And so these are different forms of aluminum oxide. The only thing that's going to be different between these guys, these quartz crystals, is their geometric pattern, which causes them to have different colors associated with it. They're the same chemical compound, but their organization is different. Now you have to talk about a geologist, he'll definitely tell you, but I think that's what it is. So this here is aluminum metal. So this here is just a metal crystal. Okay, so ionic crystals, these are all examples of ionic crystals. So where you just form your ionic compound, and then they're going to form a crystalline structures. So these are properties. They're going to have high melting points. They're generally water soluble, not always, but generally. They're going to be brittle. They're going to be able to conduct electricity only when they're melted or dissolved in water. So molecular crystals. So these guys are going to be low melting. They're usually more soluble in organic solvents rather than water. They usually don't conduct electricity, so they're non-conductors in their pure states. So networks, so silicon oxide and carbon. So these guys are going to be very high melting. They're going to be insoluble in most common solvents. They're going to be brittle. They're also going to be either non-conductive or they're going to be semiconductive. Metallic. So these guys are going to have a wide range of melting points. They're usually insoluble in most solvents. They're going to be malleable, ductile. Malleable basically means that you can kind of malleable is kind of like you can like bend them and things like that when they're like thin and stuff like that. Where ductile means that you can kind of stretch them out to like wire-ish forms. And they're usually good at conducting electricity. So. Okay, so how are we doing? How are you guys doing now? Brain still working? What time is it?
Kinda.
Kinda?
Not really.
Not really? Have you tapped out?
Close to.
Yeah. Well, we have 15 more slides. I'll try to get it done pretty fast. So the next part is the heat. Okay, so we talked about energy and, at the very, very beginning of the semester, but the way that we're going to define energy is going to be based upon the enthalpy. And that's just going to be basically Q. Q represents that heat that's going to be associated with stuff, and or the energy that's going to be required. So the energy that's going to be required is going to be equal to the heat of vaporization times the mass. Okay, so that means that the heat of vaporization, its unit is just going to be kilojoules per gram, typically. Sometimes they'll put it kilojoules per mole, but we know we can convert that. Okay. And so, again, this is just called the heat of vaporization. Now, the condensation would be exactly the same thing. Only thing is, it would be delta H condensation is equal to Q over M. Okay, so the heat of fusion. Now, the heat of fusion is that part of going from liquid to a solid. So, or what we refer to as freezing, right? So the heat of fusion, this represents the heat of fusion. This here is the heat of vaporization. I'm surprised I didn't say anything. Okay, so how much energy is needed to vaporize 188 grams of a liquid if its heat of vaporization is 1.13 grams? So we know that Q, that energy is going to be equal to delta HV times M. Okay, so in this case, 188 grams times 1.13 kJ per G. So grams are going to cancel out, and then Q is just going to equal
212 kilojoules.
Okay. Simple. Okay, so the heat of fusion, so that is going to be delta H fuse times mass is equal to Q. Same concept, exactly the same thing. No, I'm sorry. Heat of fusion is when you're going from a solid to a gas. Solid to a liquid, not solid to a gas. That's going to be heat of fusion. And then the heat of solidification is going from a liquid to a solid. And these values are going to be equal to each other. Okay, so how much energy is it required to melt 25 grams of ice at 0 degrees Celsius? Okay, so the way we would figure that out is if we go back to that table, water, okay, heat of fusion, 3. Or 333. Come on. So it's 333, and that was joules per gram times 25 grams.
Would it be 8.33 kilojoules? Or what's the preferred? Is it preferred in kilojoules or joules?
It's preferred in kilojoules.
Okay.
And we know that it would be 8,330 joules. And we just divide that by 1,000 to get kilojoules. Okay. Piece of cake. Okay, now specific heat. Specific heat is looking at the, let's see, okay, so you guys cook, right?
Yes.
Okay. You use a piece of metal when you cook, or a pan, right?
Yes.
Yeah, like iron or copper.
That's right.
Like
So you either
skillet.
use, yes, so you use iron, copper, or aluminum, right? So based upon the type of metal you have, it's going to be able to conduct heat through it, right? Some are going to be better than others, right? So specific heat is looking at that heat flow over that substance, okay? So how much heat is going to be able to be transferred through that substance that we're looking at. So the way that we would calculate the energy that's going to be associated with that is Q equal to M cat, M delta T, where that C represents that specific, it's called specific heat. And there's tables that gives us the specific heat for everything, okay? Now we have specific heat for like water and ice and all that stuff. So if we're talking about ranges, we're looking at how heat is being conducted in that fluid over that given temperature range. And so we need to be aware of whether we have ice, liquid, or solid when we take that in consideration, okay? So let me show you what I mean. Hold on. Okay, so this is aluminum. This is the specific heat for aluminum. This is the specific heat for diamond. This is for copper. This is for gold. Here, this is the specific heat for iron. This is the specific heat for silicone, sulfur. And these are the specific heat for compounds like water in the ice form, so ice, liquid, and steam. So those are the specific heats. Now these values, they're in joules per gram Celsius. They can also be joules per gram Kelvin, because that change in temperature is going to be the same regardless of whether it's Kelvin or Celsius, not if it's Fahrenheit. Okay. So how much energy is required to change the temperature of water from 10 degrees to 50 degrees Celsius? So the way we would do that is we're going to use Q equals MCAT, M delta T. Okay, where T is going to be going from 10 degrees to 50 degrees. So that delta T is going to equal T final minus T initial. Okay. We know that M in this case is 25 degrees. And let's go back to that table and get C.
What's the form of the water?
It's what is the form of water when it's from 0 degrees Celsius to.
Oh, I see. Yeah.
So that's why you need to pay attention to the temperature. So we know that it's a liquid.
It's a liquid.
Yeah. So C is going to be equal to 4.18. And that's going to be joules per degree Celsius, grams. Okay. So we just plug all those in. Let's do 50 minus 10. $25 degrees. I mean, 25, yeah. Being lazy here. I'm also having trouble with my point. There we go. Our C is going to be 4.18 joules per C grams. And then that's times 40 degrees Celsius. Okay. So what you guys got? Okay. Now, if we're looking at substance and we're starting with ice and we're going all the way to steam, we have to take in consideration everything that's happening. Okay. So let me give you an example. I love this question. So here we're starting with a solid. So we're starting with ice. So we're starting below 0 degrees. We're going all the way up to 0 degrees. So this is where ice starts to melt. Now this here is that change from that value that's below 0 degrees to 0 degrees. So that's going to be dictated by this equation. Okay. Now going from melting to start, going from that solid to melting, it has to get over what we call a hump, a threshold. So that's going to be dictated by that heat of fusion, right? So we need enough energy to get over that threshold. And then we're able to start melting. If we don't have enough energy to get over that threshold, then we're going to stay at that melting point. Okay. So then it's going to stay at 0 degrees temperature, right? 0 degrees Celsius if it's ice. Okay. So this here is going to be dictated by Q is going to be equal the mass times the heat of fusion. And then once we start melting, it's going to go from the temperature change that we have. That's going to be dictated by Q equal to MC delta T. And then again, when we get to boiling, we're going to have to get over our threshold energy, where we have to put enough energy in to get over that heat of vaporization. And then that's going to allow us to get into the gas phase, to our final point. Now, altogether, if we're starting from this point, going to this point, we have to take into account all of these equations. Okay, I like questions like this because it takes everything into consideration. So if we're starting at a negative 10 degrees, and let's say we have 25 grams of ice, and we want to get it to 110 degrees, then we're going to have to take into account all of these equations, right? We know that the MC of liquid is different than the the C of liquid is different than the C of a solid, which is different than the C of gas, okay? The mass is going to be the same for all of these, right? So the only thing that's going to be changing are the C's and that delta T. Here we're going to have that delta H. The delta H for fusion is going to be different than the delta H for vapor. Okay. Okay. So here's an example. Calculate the total heat transfer when 16.6 grams of ice, initially at negative 12 degrees Celsius, is heated to steam at 115 degrees Celsius. Okay. So let's get all of the components that we're going to need. Let's get all of our C's and all of our heat of fusion from our tables. So I'm going to write up here at the top what we want. We're going to go get C ice. C liquid. And then C gas. We're going to need delta H fusion. And we're going to need delta H vape. So I'm just going to put V for short. Okay, so let's go collect those on our back slides, because I don't have them memorized in the top of my head. Oops, got carried away. Okay, so here's our C's. So that's C ice. 2.06, and that's joules, grams, Celsius. Our C liquid is 4.18, and that's joules, grams Celsius. And our C gas, oops, is 2.00 joules grams Celsius. Okay, heat of vaporization of water. And the heat of fusion. So that's 3 joules grams. And this is 2.26 kilojoules per gram. Okay, so now we could go back to our problem. We have everything that we need. And usually they're going to be given to you in the problem on your exam. So you're going to have a table with everything. Okay. So what I always like doing is drawing out what I'm doing, right? So this is going to represent the temperature. This is what I think is going to be happening. Okay. So from negative 12 to 0. Okay. So that's just going to go up because at 0 is where ice starts to melt, right? So, and then we're going to have to come over that hump. Okay. And then from 0 to 100 degrees, that's going to be a liquid phase, right? So we're going to go up. Then at 100 degrees, that's when water starts to boil. Okay, then we're going to have that little table. And then we're going to go up to 115. Okay, so that's 115. Okay, so this first part, that's going to be dictated. I'm going to call this A. Let me put in different colors. Anybody colorblind?
No.
Well, it doesn't matter. We're going to use letters too. A, this is going to be B. This is going to be C. This is going to be D. And this is going to be F. Okay, so for A, that's going to be dictated by Q equals M C ice delta T. Okay, so let's go ahead and plug that in. M is going to be 19.6. Our C, ice, is 2.06. Grams Celsius. And our delta T is going to be 0 minus 12. Oops. Okay, so then Q is going to equal, for A, think we're going to stop after this. Although, no, now we're not, because there's 3 more slides. So
Would it be 485 joules? Is that, did I get that right?
okay, let's see. 19.6 times 2.06 times 12. Yep, 485. Okay, now B is just going to be the mass. Q is going to equal the mass times delta H vape. Oops, sorry, not delta H vape. Got carried away. Delta H fusion. Fuse. Okay, so delta H fusion. So we have 19.6 grams times 333 joules per gram. And so that's going to equal
6,530 joules.
6,530 joules. And C is going to equal Q equal to MC, in this case, liquid, delta T, which is going to be equal to 19.6. Come on. Times 4.18. That's joules per Celsius grams. And that change in temperature, which is going from 0 to 100. So 100 minus 0, which is just 100 times 100. And that equals
8,190 joules.
8,190. And D, which is going to be Q equal to mass delta H vape, which is going to be equal to 19.6 it's bad. I can't read my own handwriting. Is that 2.26? Oops. 2.26 kilojoules per gram.
Oh, so that would that be let's see, 44.3 kilojoules.
44.3 kilojoules. Okay. And then not F, that should be E. E equals Q. Oops. So I said Q equals MC gas delta T. So now we have 19.6 times 2.00, and that's joules per gram, times delta T, which is 115 minus 100, which is just 15.
And I got 588 joules.
Okay, so then we need to add them all together. We need to make sure that they're all in the same units. So either we have to change everything to kilojoules or change everything to joules. It might be easier to change everything to kilojoules. So we know if we just divide this by 1,000, so we'll have 485. So that'll be 0.85 plus 6.530 plus 8.190 plus 44.3 plus 0.588. That's going to be our total Q. Total. So Q total equals
60.1 kilojoules. Yeah.
Okay, questions? Cash, Kool-Aid. No questions?
And then would it be the same amount of energy to freeze it back?
Yeah. That's right. Exactly the same amount. Only thing in that case, it would be a negative value rather than a positive value. Yep. Okay. So this is just showing you everything broken down, A, B, C, D, E, and F. And so you guys get to see the different phases. And then this is just doing that each one independently. Okay. Questions? Concerns? Cash? Kool-Aid? We're done.